Hello everyone, I'm Lovely Kogina, final year chemical engineering student at VNIT Nagpur. Today, I will be introducing you to the topic rotational viscometers, a robust tool for industrial success. So, in this video, I will be initially discussing what is viscosity, what are viscometers and why we are studying them, theory related to viscometers, and our main topic rotational viscometers, in which I will be discussing working principle of rotational viscometers, its fundamental components, procedure, that is how to use them, output analysis, advantages and limitations, applications, and finally conclusion. Let's dive in. What is viscosity? So, in general, viscosity refers to how thick a fluid is and how easily it flows. In scientific terms, viscosity is the measure of a fluid's internal flow resistance. This resistance is the resistance that a fluid shows when being deformed or when force is applied. For example, let us consider two fluids as you can see in the picture here. One is water and another is honey. If you try to pour honey and water from bottle into a cup, you can see that water flows very easily compared to the honey. By seeing, we can come to a straight conclusion that since honey is thicker, it takes time to flow compared to the water. In scientific terms, we can say that honey has more internal resistance than water. If we look into the numbers, viscosity of water at 20 degrees Celsius is 0.01 centipoise, whereas viscosity of honey at the same temperature is 10,000 centipoise. So from this we can come to a conclusion that honey has more resistance, so that's why it has more viscosity, whereas water has less resistance, that is the reason for its less viscosity. So what are viscometers? In general, a viscometer is an instrument that is used to measure the viscosity of the fluid. It is also known as viscosimeter. Viscometer only measures under one flow condition. So here one flow condition represents that viscometers measures the constant viscosity of a fluid, like the fluid which you are measuring or the sample which you are measuring, the flow condition should be constant. Only at that case viscometers are used. Otherwise, you can use another instrument called rheometer where the flow conditions keep on changing. Now, why viscometers? Like you should have a point now why you are seeing this video. As a chemical engineer, after completing your studies, when you get a job, you will join an industry, be it any industry like oil and gas industry or a cosmetic industry or a pharmaceutical or a food industry. In any industry, viscometers are used. These viscometers are used for viscosity testing, which is one of the most important methods used to check the quality of materials. Like if you want to check the quality of the raw materials or you want to check the quality of the sample in the manufacturing process or at the end of the manufacturing process, that is for the product, these viscometers can be used. Now we will see theory related to viscometers. There is a formula for measuring viscosity, that is it is the ratio of shear stress to shear rate, where shear stress is the force per unit area that you need to move one layer of fluid in relation to another, where shear rate is the measure of change in speed in the movement of intermediate layers in respect of each other. The units of viscosity are centipoise or pascal second. Centipoise is equal to 1 millipascal second. For many liquids, the stress that causes flow is directly proportional to the rate of shear strain. The shear stress divided by the shear rate is constant for a given fluid at a specific temperature. This constant is the dynamic or absolute viscosity, but you can also simply refer to it as the viscosity of a material. There is another type of viscosity called kinematic viscosity. To measure this kinematic viscosity, we need a device called rheometers. So, in general, viscometers are broadly classified into three types: capillary viscometer, falling and rising body apparatus, rotational viscometers. Each of these viscometers are subdivided into many types. In this video, we will see in general what are rotational viscometers and its applications, its advantages and limitations, its fundamental components also. So, In general, rotational viscometers measures the viscosity of the sample by turning a spindle into a cup. So here spindle is the component which rotates in the cup. So this is the component which distinguishes the rotational viscometers from the other types of viscometers. Also, viscosity testing with rotational viscometers is suitable for everything from liquid samples to semi-solid ones. These viscometers are suitable for both Newtonian and non-Newtonian fluids. So, for Newtonian fluids, the viscosity remains constant regardless of change to the shear rate. Examples of typical Newtonian fluids include water and motor oil. But in non-Newtonian fluids, the viscosity fluctuates. These fluids include the types like plastic, pseudoplastic, rheopatic, thioxytropic, and dilatant. An everyday example of a non-Newtonian fluid is tomato ketchup, which when you shake the bottle, it becomes random. Generally, all the viscometers only measures fluids which are Newtonian. But rotational viscometers can measure both Newtonian and non-Newtonian fluids. Working principle of rotational viscometers. Rotational viscometry works by measuring how much resistance a rotating element faces as it moves through a fluid. This resistance is directly related to the fluid's viscosity and it is expressed in terms of percentage of torque. By analyzing the relationship between torque and angular velocity, rotational viscometers can provide quantitative information about the fluid's viscosity and its fluid properties. To understand the working principle of rotational viscometer in detail, we will first see the fundamental components, then the procedure. Then you can get a clear idea about the working principle of the rotational viscometers. So here in this picture you can see a general representation of a rotational viscometers. So these are the components rotational viscometers generally consist of. The first one is motor, calibrated spring, guard arm, temperature probe, spindle, beaker with sample. In this picture another one is missing, that is user interface. Now we will discuss these fundamental components one by one in detail. Spindle or rotor. So this spindle is the part that is submerged in the sample fluid. As I earlier said that this is the component which distinguishes rotational viscometer from the rest of the viscometers. It rotates at a set speed and the resistance exerted by the fluid on the spindle is measured to determine the viscosity. There are different types and size of spindles which are used depending on the sample you are using and the type of measurement needed. The next component is beaker or sample holder. So here the beaker contains the fluid sample whose viscosity is being measured. In the experiment, we have to make sure that the beaker which contains the sample is in a stable position so that we can get accurate and repeatable measurements. So our next component is motor. So this motor provides the, or you can say drives the rotational motion of the spindle at a set speed. The speed of rotation can be adjusted to analyze how the fluid's viscosity changes under different shear rates, which is especially important for non-Newtonian fluids. The motor stability ensures accurate and consistent readings. So, our next component is calibrated spring. The calibrated spring measures the resistance or torque exerted by the fluid on the spindle. As the fluid resists the rotation of the spindle, the spring deflects. The degree of deflection is proportional to the fluid's viscosity and this deflection is used to calculate the viscosity. Our next component is guard arm. This guard arm stabilizes the spindle and protects it from excessive vibration or shocks. This ensures that readings are accurate and that the spindle remains aligned with this sample fluid. Our next component is temperature probe. Temperature has a significant impact on viscosity, so the temperature probe measures the sample's temperature to ensure accurate readings. Our next component is user interface. So this user interface is different for different viscometers. Like if we take digital rotational viscometers, for this type of viscometers, the measured values of viscosity are directly displayed. Like there is no need to do calculations, and it also allows configuration of settings. Whereas when we see a dial rotational viscometers, it displays the measured torque percentage, and it also allows configuration of settings, but we have to do some calculations or data analysis to obtain the viscosity values. So from these components we can understand how the rotational viscometers in general works. Like uh, first we will take the sample in a beaker. Next we will decide what spindle we have to use based on the literature we have. Like you have to go through the literature for deciding what spindle you have to use. After deciding the spindle, then you have to set the rotational speed. So like this rotational speed can be set by fixing at what shear stress you want to measure the viscosity. And next you have to switch on the motor. In that way we will get the viscosity values at a particular shear stress. Now we will see the general procedure on how to use a rotational viscometer. First is sample preparation. So before using any kind of instrument, we have to make sure that the sample we are using is free from impurities, contaminants or air bubbles. To make sure that it doesn't contain any kind of impurities, we will involve the sample into processes like filtration, degassing or centrifugation, so that we can obtain a sample which is uniform and stable. The next is temperature control. As we all know that viscosity is temperature sensitive. So while using the viscometers, we have to make sure that the temperature is constant during the experiment. To achieve this, we use a temperature controlled viscometer, or we place the device in a temperature controlled environment so that we can get the true viscosity at that particular temperature. Next is measurement procedure. In that, first we have to select the appropriate rotating element. As I discussed it before, rotating elements can be selected based on the type of sample we are using and the measurement requirements. For this, we have to go through the literature which is available for the rotational viscometers and the spindles which we are using. Next, we have to set the rotational speed. The speed is set according to the sample shear rate requirements. Correct speed setting ensures that the fluid is tested under appropriate conditions, providing accurate viscosity data. Next, we have to measure the torque and angular velocity. These values are essential for calculating viscosity, especially for fluids that do not have a constant viscosity. Like if we use an advanced rotational viscometers, we can directly get these values, means these values are directly displayed on the user interface. But if you use the traditional viscometers which has a dial in it, then we have to do calculations manually. Our next step is data analysis. In this, the raw data, that is torque and angular velocity collected from a rotational viscometer, needs to be carefully analyzed to ensure accuracy and identify any potential errors or outliers. Statistical methods are used to interpret the data and assess the viscosity in relation to variables like shear rate and temperature. Our next step is rotational viscometer calibration. Calibration is crucial to ensure the accuracy and consistency of measurements. Calibration can be performed by using a fluid with a known viscosity or by using a viscometer equipped with an internal calibration system. If we are using an advanced rotational viscometers, then it contains internal calibration system which eliminates the need to go for a fluid which viscosity is known. Our next step is output analysis, which is the important step. So for different types of rotational viscometers, there is different types of outputs which we obtain. Our first type of output is viscosity values. In current situation, the viscometers, means the rotational viscometers used, directly display the viscosity readings in units such as centipoise or Pascal seconds. So this eliminates the need of calculating the values manually. Next is torque or shear stress. If we are using any traditional type of viscometers, that is the viscometers like dial rotational viscometers, then the output is displayed as torque percentage. That is, torque is usually displayed as percentage of the viscometer's maximum capacity. For this, you have to use a formula to obtain the viscosity values. That is, apparent viscosity is equals to A multiplied by K multiplied by L divided by 1000, where A is the coefficient depending on the torque module of the viscometer, K is the coefficient depending on the rotational speed by spindle combination, and L is the value read on the dial. So for obtaining the value of A, while purchasing the viscometer itself, you have to collect the data from the vendor, like what is the coefficient for this torque model. Next, for obtaining the value of K, you have to go through the literature, like you have to make sure that what type of rotational speed you are setting and what type of spindle you are using. And next, for the value of K, which is the value read on the dial, like here you can see the image of a traditional rotational viscometer, that is dial rotational viscometer. So here you can see a red line, right? So this red line represents the value of the dial. That is, here you can say it is pointed at 80 degrees. From this we can say that the percentage of torque for the sample which is being measured is 80. Our next output is viscosity versus shear rate graphs. So this viscosity versus shear rate graphs are particularly useful for non-Newtonian fluids where viscosity changes with shear rate. And our next output is temperature dependent viscosity data. This is valuable for applications sensitive to temperature variations like lubricants and polymers. So here you can see a graph. This graph represents rotational viscosity in terms of temperature. So this graph is for a polymers. Here you can see that the black line represents the polymer called pen 60 by 70 and red line represents KLA and blue line represents CLA. So here you can say that at temperature 135 degrees Celsius, all elements have a higher rotational viscosity compared to the temperature at 160 degrees Celsius. Now here there is another graph where the viscosity is being measured with respect to time at different rotational speed. So you can say that for 80 rpm the viscosity is constant with respect to time, like there is no much significant change, whereas for 200 rpm you can say that the viscosity keeps on increasing with the time, and same goes for 250 rpm also. Now we will see the advantages and limitations of rotational viscometers. So the first advantage is it is versatile. It is available for a wide range of configuration. Next, it has high precision and accuracy. Like the rotational viscometers provides results with high precision and accuracy. It allows shear rate control and adjustment. Next, it is easy to use. As you can see that the fundamental components is easy and the procedure is also easy. Now coming to limitations, it is sensitive to temperature. Like if you are not using a advanced rotational viscometer or you are using a traditional viscometers, you should make sure that the temperature is constant. Next, it is limited to shear rate range. The next limitation is sample volume requirements. That is, at a particular time you can use only a particular amount of sample. The next limitation is maintenance and calibration. Now we will see the applications of rotational viscometers. As I before discussed, there are many applications of rotational viscometers. The first one is quality control and process monitoring. That is, as I said, viscosity testing is one of the important methods which is used for the checking of quality of products. Next is research and development. In research and development also viscosity testing is used to check the final quality of the product. Next is lubricant and fuel testing, and the next application is coating and ink formulation. And in biomedical and pharmaceutical industries also rotational viscometers are used. And the last is food and beverage processing industries. So till now we discussed about what is viscosity, what are viscometers and why we are studying them, and in detail about the rotational viscometers and their applications. From all this we can say that rotational viscometers are more than just scientific instruments. They are robust tools that can directly impact industrial success. By providing precise measurements of fluid viscosity, these devices help manufacturers ensure product quality, optimize production process, and develop innovative new materials. So these are the references that I used for collecting the data which I presented in this today's video. Thank you for watching the video.